Hello all, today we will see how to make stability analysis in time domain using Routh Hurwitz criteria. Initially, I have listed the methodology, the rule set which is to be followed for writing the Routh array and accordingly solve the numerical. And in the second half of the slide, the stability prediction criteria is defined. We will see methodology and stability prediction for the Routh Hurwitz criteria using numerical. So let us focus on the numerical first. So the question is, the open loop transfer function of a unity feedback system is g of s is equal to 5 upon s to the power 4 plus 8s cube plus 18s square plus 16s. Using Routh criteria, determine stability of a system. We'll begin with the solution. In the methodology, the first step was deriving the characteristic equation or writing the characteristic equation. Now here, from the numerical, it is clear that the gain of the feedback system is unity. That means h of s of the system is 1. And g of s is given as 5 upon s to the power 4 plus 8s cube plus 18s square plus 16s. So we have g of s and h of s available from step number 1 or from the given data. So from this, we need to find out the characteristic equation. Characteristic equation is denominator of closed loop transfer function, or the characteristic equation can be 1 plus minus g of s h of s equal to 0. So first task is to find out the characteristic equation using any of the formula. We may use the feedback rule to define the closed loop transfer function, assuming that h of s is 1 and g of s is this given data. Or 1 plus g of s h of s equal to 0 can be used to determine to write the characteristic polynomial. Here by default we are assuming that the feedback is negative and therefore 1 plus g of s h of s equal to 0 is the characteristic equation, a generalized characteristic equation. Now using this formula we are writing the characteristic equation of the given system. So 1 plus 5 upon s to the power 4 plus 8s cube plus 18s square plus 16s equal to 0. Make the denominator common. Therefore, the polynomial will be s to the power 4 plus 8s cube plus 18s square plus 16s plus 5 equal to 0, and this is our characteristic equation for the given g of s h of s. This is what is step number 1. Step number 1 says to write the characteristic equation from the given data. Now we'll come to the step 2. According to the methodology, step 2 is forming the Routh array. Now what is Routh array? Routh array is a table of rows and columns. The number of rows and number of columns will depend upon the polynomial obtained in the step 1 or the characteristic equation obtained in the step 1. The first two rows of the array are actually written from the characteristic equation. The first row of the Routh array is always the highest degree of s in the polynomial. Since the highest degree here in the polynomial is s to the power 4, the first row of the Routh array is s to the power 4. And in the next subsequent columns of that row, we are supposed to write down the coefficient associated with s to the power 4, s to the power 2, s to the power 0. So, in the s raised to 4th row, that is the first row of Routh array, in the first column, we will write the coefficient of s to the power 4 from the characteristic equation. What is s to the power 4th coefficient in the polynomial? 1. So that 1 is mentioned here in the first column of the first row. The second element in the first row is the coefficient of s square. What is coefficient of s square? 18. So that 18 number is mentioned in the second column of the first row. The next element in the third column is the coefficient of s to the power 0. S to the power 0 is 1 and therefore the 5 is the element to be written in column 3 of the first row. This is how the first row is mentioned. First row is written. Now if for an example, let's take a second example that the highest degree in the polynomial obtained for an example, let's say s raised to 5. So your first row of the array will be s to the power 5. The coefficient here will be s to the power 5 coefficient. The coefficient in the second column will be s cube coefficient. The coefficient in the next column will be s to the power 1 coefficient. So this row will depend upon, these rows selection will depend upon the characteristic equation. Okay, now we'll write the second row of the element, second row of the array. The second row of the array will be the 1 degree less s. That is, the first row is s to the power 4, second row is s cube row. And again in the subsequent columns, we have to write the coefficient associated with s cube, coefficient associated with s to the power 1. Means what? In the second row, s cube row, the first column will be the coefficient of s cube. So let's go to the polynomial. The s cube coefficient is 8. So that 8 number is mentioned in the first column. The next second column will be the coefficient of s to the power 1. S to the power 1 means s, and the coefficient of s is 16. So that's why the 16 is mentioned in the second column. This is how the Routh array, the first two rows of the arrays are formed. This is what we have to do in the step number 2. Now further, in each row, the power of s has to be reduced and the computation has to be done. So we'll see how to do that in step number 3. So let's go to step number 3. Now, the first two steps are written from the Routh array, first two steps are written from the characteristic equation. Now we have to write the next row. The next row will be obviously s² row. Now this s² row needs to be calculated, needs to be computed. Now how to do that? We'll see only the first element here, the first column here. In the s² row, the first column element will be written with some diagonal multiplication. What is the diagonal multiplication? We have to do the multiplication in such a way that 8 into 18 minus 16 into 1 minus 16 into 1 and this whole divided by the number here, that is 8 divided by 8. So if you calculate this 8 into 16 minus 1 into 16 divided by 8, it comes out to be 16. This is how the first element of s² row is calculated, defined. Now let us go to the second element here. Same row, second element. The second element is calculated as, again we'll take the first column element of s³ row, that is 8 into 5 minus 0 into 1, and this entire divided by this base element, that's an 8, divided by 8. So we have 8 into 5, 40, minus 0 into 1, 0, means 40 minus 0 is 40, and divided by 8, it comes out to be 5. So now we have the elements in the first and second column of s² as 16 and 5 respectively. And these 16 and 5 are determined by the diagonal multiplication. Okay, now let us go and find out the next row. The next row will be s to the power 1th row, because we have obtained s² coefficient, s² elements. Now next row is s to the power 1th row. So we'll see how to determine the coefficient in s to the power 1th row. That's an s row. So let us go. Let's see. Okay, now we are about to find out the coefficients or the elements to be mentioned, to be written in the s to the power 1th row. For calculation of the s to the power 1th row, we'll take the help of s² and s³ row and we'll write the values. The same methodology will be followed. For writing the element in this column, we'll have a multiplication of 16 into 16, same methodology as we have done in the earlier case. 16 into 16 minus 5 into 8, and this entire divided by this base element, that's a 16. So 16 into 16, 256, minus 5 into 8, 40, complete divided by 16, and this comes out to be 13.5. The same method will be now used for calculation of the second element in that row, second column element of s to the power 1th row. How to do that? 16 into 0 minus 0 into 8 divided by this base element 16. So 16 into 0 is 0, minus 0 into 8 is 0, 0 minus 0 is 0, 0 divided by 16 is 0. This is how the s raised to 1th row is calculated. The same procedure will be used again to find out the s raised to 0th row. Remember, we have to do this process unless and until we reach to s power 0th. S power 0th is the last row of Routh array. So let us go and find out the S to the power 0th row. So let us go and find out the S to the power 0th row. So this is S to the power 0th row. The element here will be calculated based on S to the power 1th row and S squared row. So how to do that? Again the same diagonal multiplication. 13.5 into 5 minus 13.5 into 5 minus 0 into 16, and this entire divided by 13.5. Entire divided by 13.5. So this entire calculation comes out to be 5. So this way, this is the complete Routh array formed, because the last row of this array is now S to the power 0th row. So once we reach to the S power 0th row, we say that the Routh table is complete. Routh array is completely designed. Now based on this, we have to make some predictions. What are those predictions? That's the last step, step number 4. We have to check the signs of all elements in the first column of the array. Now the first column is of importance, and the sign of each element in that first column in the rows we have to check. So the first element here in the S raised to 4th row is 1 and it's positive. The second element in the array is 8 and that's a positive. The third element in the first column is 16 and it's a positive number. The next element 13.5 in the first column is positive number. And the last element in the S raised to 0th row of the first column is 5 and it's also positive. If all the elements in the first column of the array are positive, now they are purposefully indicated into a circle for clear understanding. Since all elements in the first column of the array are positive, we say that the system is stable. We say that the system is stable. And this is what is defined there in the first slide in the system stability prediction. If all elements in the first column of the array are positive, we say that the system is stable. There may be cases that the element in the first column may be negative. A particular element may have a negative sign. In such cases, the stable system is said to be an unstable, and the instability will have some number of poles lying in the right side of the system. Once we say that the system is stable, we mean to say that all poles of the systems are lying in the left half of the S-plane. We'll see one more example and we'll find out whether the system is stable or not. We'll specifically focus on the unstable state of system. So in the next coming video, we'll see how to find out the stability of a system wherein the first column of the array is a negative.